Thanks for the listening of the presentation of the paper with the title Hierarchical Rendering System Based on the Viewpoint Prediction in Virtual Reality. And I'm the presenter. This work is the collaboration between the ZT Corporation, the Hong Kong Polytechnic University, and also the University of Sydney, and also Shanghai Jiao University, and the Shanghai University of Sports. The research background is that during the implementation of our VR system, we found that the user may look at different objects of the interest or in different direction of the contents when we rendering them in our HMD, the headsets. And usually when we design the system, the field of view of the human vision is 135 degree multiply 160 degree. But actually, the one requiring the highest resolution is only in a small area, like 1.5 degree multiply 2 degree. It will introduce a problem that for in headsets HMD, only the 4% of all pixel resources are really mapped to the visual sensor, and it will introduce a lot of the resource useless or waste. And also, in the current VR headsets, the eye tracker, the hardware module, is very expensive and really hard to use. Given the above discovery, and we implement our system and introduced some principles to help to improve the user experience. As mentioned in these pages, it is the main part of our paper. First is that we introduce an eye-head coordination model, which combined with the saliency of the scenes to predict the gaze position. And the second, based on the above results, we really introduced a hybrid method of level of details. Given this level of details, and we also introduced the grid degeneration to help reduce the rendering time, so we can improve the overall system performance and the user experience. The whole system contribution is as below. Firstly, the model based on the eye-head coordination compared with the previous work has fewer limitations and also can be better to meet the real-time viewpoint rendering requirement of VR applications. Secondly, we adopted a hybrid method of level of details and introduced the mesh degeneracy. We only use the retained vertex as the skeleton, and also we save separately the simplified model and also the original model. During the rendering process, only the mesh near the viewpoint is merged back with the original model, which we can improve the position of the area near the viewpoint and also decrease the computing efficiency. This work is based on some previous work which we have been carrying out. The first is a model for viewpoint prediction in the immersive video, and the second is obtained the correlation between the head movement and eye position. The whole system structure is illustrated as the below figure. The whole system can be divided into 5 parts. Firstly is that the model has been loaded and performed some simplified model calculation. And the second one is that one or more simplified model are generated for each object. And the third one is that actually the when the viewpoint prediction algorithm is performed, which we introduced some level of details, and this is given our later rendering process. And the one during the rendering process, the model stitching steps will based on the predicted viewpoint, the information, and also the model and the original, and also the simplified model, and then combine this to the rendering calculation. As we mentioned previously, we improved the viewpoint prediction and reached some real-time performance and improved also some efficiency. And it is introduced by firstly, we separate the horizontal and vertical calculation. And second, in order to improve the effects of this algorithm, we combine the angular velocity and angular acceleration of the head movement, and also the delay of the eye movement, and also the header movement contains tasks and other facts together, as the below calculation has illustrated. This is also these two facts, and also give us a good results of the viewpoint prediction in the higher real-time efficiency. The scheme of the implementation of our system is that we introduce the hierarchy rendering in our rendering process. This is with benefits is introduced by firstly when we loading our module, we simplify the model mesh according to different levels of details. And during the simplification of each level, we save the simplified model and also the changed vertices and faces as the resources of our later rendering process. And during the rendering process, when we stitching the algorithm is performed, we can, based on the predicted gaze position, and to organize all this original model and the simplified model the resource. We implement our system with the help of Unity and also the model degeneration process. And we set up the experiment to help to verify the effects and efficiency of our system and implementation. During the experiment, we also recorded our CPU usage, GPU usage, and the video memory usage, and also the system memory usage. Below is two fingers as listed also on our papers. First one is without hierarchy rendering, and the second one is with the hierarchy rendering, and we can see the difference. Here we list the results under different settings to show the effects and the efficiency of this system design. And we can see we list the status and the statistics of the CPU, GPU memory, and the video memory. And according to the data in the table 1, we can see that the CPU usage has been increased because of the process when we returning new triangles to Unity. And also the memory usage has increased because of the simplified algorithm saved incremental data. And the third, the video memory usage is also increased because our system maybe triggered a certain cache mechanism of the GPU. Above is all my paper presentation, and thanks for your listening. And later is the time for question. Thanks you.